to 1. So for that, in that case we have to check individually, right? For mod x equal to 1. Now for mod x equal to 1, that means what? There are two cases for mod x equal to 1. Either x is equal to 1 or x is equal to minus 1. In both the case we have to check. So the first case 1, that is x equal to 1, right? Now you can see the x equal to 1. What is our example? This is our example. Minus 1 raised to n minus 1, x raised to 2n minus 1 upon 2n minus 1. Now put x equal to 1 here. Put x is equal to 1. So that will become, this term will be cancelled out, right? Now when x is equal to 1, and now our series is starting from n is equal to 1 to infinite. So put the value n is equal to 1. For n is equal to 1, minus 1 raised to 0, that will become 1. This is 2 minus 1, so 1. So the first term is 1. When x is equal to 1, the first term is 1. Now what is the second term? Put n is equal to 2. So minus 1 raised to 1, 2 minus 1, that is 1. Minus 1 raised to 1 minus 1 upon 4, 2 into 2, 4 minus 1, 3. So minus 1 upon 3. So 1, the first term is 1, the second term is minus 1 upon 3. Let's check third term. Put n is equal to 3. So 3 minus 1, 2. So minus 1 square, that is 1. And this is 3 into 2, 6. Minus 1, 5. So the series is now 1 minus 1 by 3 plus 1 by 5, right? When x is equal to 1, the series is 1 minus 1 by 3 plus 1 upon 5. You can also check that the fourth term of this series is 1 upon 7, right? For this series we have to check individually, right? And we cannot apply here a ratio test, because when we, okay, so this is alternating series. This is a alternating series. Okay, now for alternating series there is also one test, call it Leibniz test. What is the test? Leibniz test. In Leibniz test, if your series u1 minus u2 plus u3 minus u4, this is alternating series, is convergent if these two conditions are satisfied. If these two conditions are satisfied, which condition? The first condition is modulus of un, that is greater than modulus of un plus 1. That means what? The nth term is bigger than the n plus 1th term. The modulus of nth term, that is bigger than the modulus of n plus 1th term. And the second condition is, as n tends to infinite, the value of un, that is equal to 0, right? Now if these two conditions are satisfied, so in Leibniz test we have to check these two conditions, that if u1 minus u2 plus u3 minus u4 is convergent if modulus of un greater than modulus of un plus 1. That means the value of modulus of nth term, that is bigger than modulus of value of n plus 1th term. And the second condition is, as n tends to infinite, modulus of un is equal to 0. And this series is convergent because of this, it satisfied both the conditions. The first condition is modulus un minus greater than modulus un plus 1. That is also possible because what is modulus un? That is 1 upon 2n minus 1. What is un plus 1? 1 upon 2n plus 1. So always 1 upon 2n minus 1 is greater than 1 upon 2n plus 1. Okay, let's check that how it can be possible. For modulus un, in this case 1 upon 2n minus 1, modulus un plus 1, that is 1 upon 2n plus 1. Now first we want to check that modulus un minus modulus un plus 1, so that is equal to 1 upon 2n minus 1 minus 1 upon 2n plus 1, so that is equal to, when we are take LCM, in denominator we get 4n square minus 1 and 2n plus 1 into 2n minus 1, so that is 2n plus 1 minus 2n minus 1, so you get 2 upon 4n square minus 1, so that is always greater than 0. And also 1 upon 2n minus 1, as n tends to infinite, 1 upon 2n minus 1, right, as n tends to infinite, if you want to check as n tends to infinite, modulus of un, that is equal to, as n tends to infinite, that is 1 upon 2n minus 1, that is also equal to 0, right. Now both the condition are satisfied, that's why for x is equal to 1, the series is convergent. The given series is convergent, right. Now the case 2, for x is equal to minus 1, case 2 for x is equal to minus 1. Now what is our series? This is our series, summation n is equal to 1 to infinite minus 1 raised to n minus 1 into x raised to 2n minus 1 upon 2n minus 1. Now when we are taking x is equal to minus 1 here, it is equal to minus 1 raised to 2n minus 1 n minus 1, so that will become 3n minus 2, right, because 2n plus n, that is 3n minus 1 minus 1, so minus 2 upon 2n minus 1, right. Now take n is equal to 1, so you will get 3 minus 2 1, so 1 upon 3, 1, the first term is 1, the second term is take n is equal to 2, so 3 into 2 6, 6 minus 2 4, so minus 1 raised to 4 is 1, right. So plus 1 upon, when n is equal to 2, 2 into 2 4, 4 minus 1 3, so 1 upon 3. Now this is minus 1, because when n is equal to 1, you can see 3 into 1, 3 minus 2, so that is 1, minus 1 raised to 1 is minus 1, when n is equal to 2 you will get 2, then minus 1 upon 5 plus 1 upon 7 and so on. So you can see this series and the previous series both are same, right, just difference is only for the sign. So when we are taking minus will be common, this series 1 minus 1 by 3 plus 1 by 5 minus 1 by 7, right. So we know that this series is divergent. Okay, already we proved that for x is equal to 1 we get this series. So we already proved that for x is equal to minus 1, for x is equal to minus 1, just changes only for the sign. So this series is divergent, this series is divergent, that means this series is also divergent, because for any convergent or divergent series, if we multiply with any fixed constant, then the result never become change. If the convergent series, for the convergent series, if we multiply with the some fixed number, that's the new series is also become convergent. For divergent series, if we multiply with some fixed number, fixed real number, then the divergence, the new series will also become divergent. So same situation happen here. This series is also divergent, this series is divergent, that we already proved. Now if we multiply with -1, that is also divergent. So for x is equal to -1, the given series is divergent. So we are solving this question paper up to this question. Thank you.